Welcome to Fun with Science, Engineering, and Technology. My name is Mr. Ross, and my assistants this morning are Scott and Andramus. And what we're going to do today is we're going to take one MCAS question, one of the sample questions from the 5th grade, and we're going to analyze that question a little bit and see what we can come up with. And this is the question. And Andramus, can you read the question?
Marcus designed a television stand like one shown below for his family. His father is worried that the stand could tip over. Look at the measurements in the drawing. How can Marcus improve the design so the stand would be less likely to tip over? A. Make the base wider. B. Make the stand taller. C. Make the top narrower. Or D. Use different material.
All right, so that's a little multiple choice question. And what do you think the answer is? You know? You know, Scott?
I say A.
You say A. Why? Make the base wider, right?
Yeah.
You remember that question?
Yep.
All right. So, all right, that's fine. It's very simple. We're done. We can go home now, right? We make the base wider. That's it. And that is the correct answer. But we need to know a little bit more than that, because you think they're going to give you this MCAS question again in the 5th grade? Or again in the 8th grade? No. They may give you a question similar to it, but not one exactly like that. Right? So what we really should know is why, when we make the base wider, does it make the stand more stable, less likely to tip over? Because what they may do is they may ask you one of those open response or essay type questions, and we have this building. You recognize that building and what that is? That's the Leaning Tower of Pisa. Not pizza, Pisa, right? In Italy, in a town called Pisa. And when they built it straight up and down, like you should build a building. But the soil was a little soft, so it started to lean. Right? Same kind of basically question is the TV stand. So why doesn't it fall over? It's leaning over. Why doesn't it just fall down?
Because of the base?
Because of the base. That's partly the right answer. But why didn't this Leaning Tower piece just, boom, it's leaning over, right? If you lean over a little bit, you might fall down, right?
Yeah.
If I take this yardstick, right, it's straight up and down now, and if I lean it over a little bit and let go of it, what happens to it?
Falls
It
down.
falls. Why doesn't that fall?
Because it's strong.
You think just because it's strong? Another question. Right, we'll let that go for the time being. Right, I have my 2 little cars over here, and if they may go around a turn real hard, real quick turn, which one is most likely to roll over?
That one.
Roll over? You think so? Scott, which one do you think?
I think that one right there.
You think this SUV or this Jeep kind of a thing is the
Yeah.
one that's probably going to roll over? Right, that's true, right? If you look at the news and so forth, they always have these stories about these SUVs being unstable and rolling over. Same idea as, if we go back to here, how do you make the TV stand more stable? Make the base wider, right? But why? Why is that car more likely to roll over? Why doesn't the Leaning Tower of Pisa fall down? And why, when we make the base wider, we make the TV stand more stable?
Because of the weight.
Because of the weight? What about the weight?
For example, this SUV, if it turns, its weight pushes it down and it just rolls over.
Okay, you think so?
Yeah.
Well, that's not a bad assumption. But let's just take yardstick. Right? This is not a meter stick, this is a yardstick. And if I take and do that, what's happening?
It's balancing.
It's balancing. Okay? And if I take and move my finger up, what happens? It goes up,
And down.
down. Okay? So, what if I put the finger over here?
It's gonna fall.
It's going to fall. If I put it over here, what's going to happen?
It's gonna
Fall.
Right, but if I go right in the middle,
It ain't gonna fall.
then it balances up, okay? And I can move it up and down, right? And if I get it exactly in the middle, it's going to stay balanced. Why is that? I'll tell you why, okay? It's because of something called the center of gravity or the center of weight. This yardstick, right, is pretty much the same all the way across, right? Pretty even. So gravity's pulling down on this end. This little piece over here weighs so much. The same little piece over on this side weighs the same, right? And if we look at the whole length of the stick, right, gravity's pulling down on all of it, okay? And it's equal amount of force over here as we have over here. Right? So if we get right in the middle, right, it's going to stay balanced. Right? And that spot right there is called the center of gravity or the center of weight, depending on whose book you're reading. Right? And I can move it up and down like this, right? And it's also the center of the mass. Remember what mass is? Right, one of the definitions that you have a mass is the amount of material in it. All right, and what it says is there's some certain amount of material here, and there's an equal amount of material on the other side. So that's where it appears all the mass is concentrated. If I take and put my finger off on the over here, what did we say happens?
It falls.
It falls, right? So we got that thing called the center of mass. It looks like all the weight is concentrated right there in that one spot. So if we were to go to one little spot right down in here, that looks like where all the weight is. If we go down in the center of the here, so we have this thing called center of gravity, center of weight, center of mass. Right? And how do we find that? If everything has a center of mass. You have one?
Yep.
Where is it? Let me see it.
Mm.
I can't see it? You're not going to show it to me? She has one too, okay? And so does my snowman. But how do we find it? That's the next question. How do we find that center of gravity or center of mass? Okay, my little snowman. It's a good thing to have a snowman because it's snowing outside today. Well, we can do that very simply. You notice I got some little strings on here, right? And I take and I get hold of one string like this. Look what happens to him. He tilts over that way, right? If I get a hold of the other string, what happens to him?
So
Tilts
tilts.
that way.
Tilts the other way. Okay. And the reason he tilts is because gravity's pulling down on him, right? And if we took my ruler, right, we said the center of mass is right in the center. There was the same amount of material on both sides, right? So I'm holding this up, right? So there must be the same amount of material over here as there is on this side. Same, equal weights from here over and here over, the weight is equal, even though the shape was funny. Right? So, Scott, what I want you to do, I want you to hold that, no, by this string, hold it up there like that. You take my place now.
Right.
Right? Now, I have a thing called a plumb bob. Right? What's happening? Gravity's pulling it straight down, right? So I know gravity, the center of the earth is right straight below this little point, okay? So you're going to be our scribe. What I'm going to do now is we're going to hold this up, okay? So that it lines up with the string. And we're going to hold it down, and you're going to put a line down along my string there. No, don't write on my finger. Okay. Now, what are you going to do next, Scott? You're in charge. The other side, right. All right? Let go. You put the pen away. Come on, we're not done yet. Okay, so I'm going to take, now, turn it around so the camera can see, and so you can, all right? So we're going to do what? We're going to draw a line right down there. All right, did you do that real careful?
No.
All right, where those two lines cross, where they intersect, right, this one's awful wiggly, right, it's probably right there, pretty close to the center. Where those two lines intersect is where the center of gravity is. or the center of weight. Because we know we do this line straight down, right? Wiggly line. It looks like a string of spaghetti, right? And you did better the first time, right? So that's going to be the center of gravity. Now, so, and it's in the page here, okay? So now then, what we want to do, I have a box, and I have some string already attached to it, so that we don't have to worry about string. Now you're going to be able to draw straight lines this time, right?
Right.
But if you hold on to this like this, it's the same as what we did with
The
the
snowman.
snowman, right? And so gravity's pulling down, and again, if I take my plumb bob and put the string down here, and you draw an X, right? Because you can do on this side too. Then we're going to find the center of gravity of our box.
Can we hold it?
Yeah, hold it.
All right.
You're the holder. You're the marker, right? Now you can't move the box, right? All right. Scott, get the other side.
All right.
No, well, let's do it this way.
All right.
Get on that one there, because we want to. We could have done either way, but that's okay. Let go of that side.
All right.
Don't. All right. So now then. Now we're getting better at this now, right?
Yeah.
Okay, so my box says the center, and the way we did it, we said the center of gravity is right there. But it's actually inside the box somewhere, right? It's back in here because we could go and we could do these edges and we'd find another spot here, and we did all the way around, and what we're doing is we can locate the center of gravity is actually inside the box, right? It's not out here on the outside. So, now, that's interesting, isn't it? There's the center of gravity. Now, if we take the box and we set it there like that, and I know you can't see the lines, but they're there. And what's it doing? It's just sitting there, right?
Yep.
But if I take it and it's like the Leaning Tower of Pisa, and I start moving it over here, and I move it over like this, that far, let go of it, what happens?
It's gonna fall back in
It
place.
goes back in place, right? Right. If I go back over here like this, it goes back in place. If I go over here like this, it goes back in place. Wonder how that is, all right? But if I go over here like this,
It'll fall.
Falls.
it's going to fall. Why? Why do you think that happens that way?
Center of gravity.
Center of gravity does something. You know it has something to do with it because we just spend a lot of time finding the center of gravity, right?
Yeah.
Right. The same thing is true of my TV stand. The center of gravity has something to do with it, whether it stands up or whether it falls. But let's watch, okay, what happens if we hold the box straight up like this, and I put my plumb bob up here, right? Where does, and let the line run through the center of gravity and the box is straight up. Where is the plumb bob? Where's the force of gravity pulling?
Down.
Down.
Straight down into the middle of this, right? Right straight down here?
Right.
It's right down there. Now, watch what happens is I move the box tilted over. Where does the center of force pull down?
Wait, like that.
It's over on the edge, right?
Yeah.
And if I go far enough, where is it?
It's
It's outside, right?
Right.
So, my box is sitting like this. The force of gravity is pulling, like you can think of it as pulling the center of gravity. All the weight is right here, pulling right straight down to the middle of the base. Okay? And as I start to tilt it, what happens? The center, the force is going towards the corner, right?
Right.
And if I go far enough, it goes past the corner, past the base. Now then, where's the force? It's not pointing. It's not pulling down straight down onto the base anymore. It's pulling down on this side. And guess what happens then?
Falls.
It falls over. So as long as the center of gravity force is down here in the base, right, it's going to be stable. It's going to stand up. So what is happening is I tilt it this way. What happens to that force? It comes down.
Pushes
It
down.
starts. It pushes down, and when I get far enough, and it pushes down and hit the spot outside the base, it's going to fall.
Right.
You know why that is? You remember levers?
Yeah.
You do? Okay. This bottom part here is just like a lever. Right, and if I tilt it this way, right, what's this? We call that the fulcrum, right?
Right.
Right, and the load would be where the center of gravity is, right? And where we're putting the input force would be where we're pulling over here to tilt it up, right? So we'll have a little lever, and if it's setting straight up and down, right? Like when they built the Eiffel Tower originally, it was straight up and down. The center of gravity is right straight down through here. And as I start tilting it, what happens? What happens to the center, where the force is for the center of gravity? It moves closer and closer and closer to the fulcrum. Right. Remember levers. If the load was closer and closer to the fulcrum, you didn't have to put as much force in it to make it go, right? You think that's true?
Mm-mm.
Yeah, that's true.
Oh, yeah.
Yeah, it is. Yeah. Look. Now let's see if that works. All right. How much does it weigh? You can't measure it with your finger over the scale.
130.
130? Is it exactly 130?
Yes.
Not even, maybe a little bit more? Okay, 130. That's pretty close. At least for my calculations. Now then, it's sitting there. What's it weigh if we don't do anything to it?
0.
0? Okay, now, I'm just going to just lift it just a little bit. What's it weigh?
1.
1? 1 what? Wait a minute. Let's do a rough. We're reading Newton's, okay.
90.
90? Right. Here it was what?
It was 130.
$130? Scott, read that for her.
That's 160.
About 160, right?
Right.
It's more than 130, right? It's bigger than 150, okay? And you say that when I pick it up just a little bit, it's what?
70.
70. So we had 150, 160 somewhere, so we got about 70, 75, depending on how close we read it, which is about half of it, right? So what that means is that my lever down here, right? I've got the load is right in the middle. My force that I'm putting in is here on the end, all right, which is twice the distance to the fulcrum is what the load is. So the force needed to lift it up is going to be like 1/2. All right, as that load moves closer and closer and closer to the fulcrum, what happens to the force we need? It's less, right? If you remember that. Who'd you have for 6th grade?
6th grade teacher, Miss Jennings.
Miss Jennings?
Yeah.
How about science?
Miss Khalil.
Miss Khalil?
Yeah.
Okay, so you did levers in science, right?
Yeah.
All right, in 6th grade. All right, so now then, what I want you to do, Scott, since she can't read,
And hold that.
I want you to lift it up very, very carefully, all right? Don't pick it up. Just pick like this. Right? What we want to do is we want to tilt it. All right. So it's
All right.
about 70 there. What's happening to it as we go over?
Tilting.
Huh? It's reading less and less, right?
Yeah.
Because what's happening to my load? It's moving closer and closer to the fulcrum, which is over here. Right now, when I get all the way over to get it really balanced up there, the force is almost zero. All right, if I go over here and it falls down, guess what's happening? So I take this and I pick it up, right, and the weight's going down here on my lever, right, and as I move it, the load moves towards this fulcrum that I have, right, and when it starts to fall, the load moves past that fulcrum, and what it's really doing is pushing down on another lever, which is this side up here, which has the same fulcrum, so it's going to make it fall down. Right?
Yeah.
Got that?
Right.
So what happens to my TV stand if we start pushing it over? Right, if we got that little itty bitty base, the center of gravity on the TV stand is up in here somewhere because of the old heavy TV sitting on top of it, right? And we assume that this is pretty light. So as we start pushing this over, right, the center of gravity is going to move so that the line of force, gravity pulling down, is going to come past the end of the base. And as soon as it does that, what's going to happen?
It's gonna fall.
Something like that box, it's going to fall over, right? So if I just make this base wider, don't do anything else, then what has to happen is I have to move the TV further and further over this way, push it over further and further, like I did with the box, before that line of force through the center of gravity gets outside the base, and then it'll fall. So that's why when we want to make that thing more stable, we'll make the base wider. Okay. Got another big box. This box is pretty symmetrical, right? And it's got pretty much the same weight all the way around distribution, same as my ruler had, right? But my snowman was a little different because he's a funny shape, right? And he's got wiggly lines on him. So now then, I've got another cylinder thing. Okay. What can you tell me? What's different about this than that?
That's bigger than that.
It's bigger than that, but what else?
Has stuff in it.
It has stuff in it. I got some modeling clay, right? So that now then, what's happened is its center of gravity or center of mass is somewhere right down in here. It's not in the center of this thing anymore. It's down in here. Can we find that? Can we find out where it's at? What do you think, Scott?
I say right.
How did we find the center of mass there?
We found it in the thing.
We did it with this and
In the
my
pen.
scribe. Scott, you hold it. All right. And let's see if we can find the center of mass here.
It's really light.
Okay, let's do the other side now.
Yeah.
Here, no, this one here. All right. Okay, that should be pretty close. Give me the pen. Give me the pen. So,
Right there.
center of mass is right there on this one. Right up here. It's not in the center anymore.
Nope.
It's up here on this end because most of the weight is over on this end. So we take this now and we set it up here like this, and we take and we move it over, right? And what's going to happen is gravity's pulling straight down on this now, and right now when it's sitting stable like that, right, it's pulling straight down to the center of the base. As I start moving the box over, what's going to happen?
It moves
It's
toward
gonna-
the edge.
It moves towards the edge, to the fulcrum, right? And eventually, when we get it over far enough,
It's gonna
It
fall.
falls.
it's going to fall. Now, if you look real careful, right, since all the weight is down there, this is going to have to move. If you look at the top of it, it's going to have to move quite a ways over before it starts to fall, right about there, right? Now then, what happens if I do this? Get the string out from underneath it because it's got to set up pretty straight. All right?
Gonna fall.
Now, center of mass is still up here, right?
Yeah.
But how far am I going to have to move it over before it falls?
Mm.
As far as I did before?
Yeah.
You think so? You see that? Watch. Doesn't have to go very far, right? Because what happens, it's all the way up here, and if I move it over, the force is down. It very quickly comes to the edge. So this way, right? I have to move it over quite a ways before it falls. Even though the two bases are the same, this base here and this end here are the same size, right? Don't have to go very far. Now, what Marcus could have done to make his TV stand stable was just turn it upside down, okay? Because we know that TV is real heavy, and we moved the center of mass all the way down to the bottom now. The only thing is, his dad would have been a little upset because he's going to have to lay down on the floor and stand on his head to be able to watch television, okay? But that's very stable, right?
Right.
This way, it's not so stable. Turn it upside down, stable. So, we take a look at these two little cars that I have. All right, this is a drag racer. All right, built down low to the ground. Where's the center of mass going to be? Down low to the ground, right?
Right.
Right. So this is going to be pretty stable. As it goes around the turn, it's not going to be able to roll over. Right?
Mm-mm.
This
That way.
SUV, in a regular, we take this and compare it to a regular car. What's going to happen to the center of mass on this one, or the center of gravity? It's going to be higher up because there's more material. This car is higher, so there's more material up here. So instead of maybe the center of mass being down here, right, it's moved up here somewhere. Right, it makes it a little unstable. So if we move the center of mass up, right, and then it's going to be unstable. One of the things we could do with this SUV is we could load it down. We could put a bunch of iron and stuff underneath it, right, and make it weigh more on the bottom, and that would move the center of mass down and make it more stable. But what would it do to our gas mileage? It would ruin our gas mileage, right? So, okay, that's it. So now then, the answer to, or the science behind this MCAS question, to which we had, the answer was very simple, right?
Yeah.
But it really isn't quite so simple. And the whole idea is that if you understand the concept, the basics behind it, right? No matter how they ask a question, whether they use a TV stand, cars, boxes, or whatever, Leaning Tower of Pisa's, you can be able to answer the question. So you got to remember those, not the answer to this question, but you got to understand and remember the answer to the basic question. Now, you know what this is?
So
Never saw one of them. What do you think we use it for, huh? Oh, what? What? It's got a runner on it. Okay? It's got a little seat on top of it. And there's snow outside.
then
And I can tuck it under my arm and carry it along with me. It's for riding in the snow. You never saw one of those before, right? Well, a lot of people have never seen it. We called these things Yankee jumpers, right? And they're all homemade, right? And the reason we call them Yankee jumpers because what you usually did, the bottom runner here, the single
Yeah.
runner is pretty wide. What we do is down at the bottom of the hill, we stack up some snow, make it like a ski jump. And so when you sit down on this thing, go down the hill, then you off, so that it's a Yankee jumper. Now, what about the stability on this? Huh? I set it up here like this, right? Where's the base? Down here, it's very narrow. Looks like Marcus's TV stand, right? So it doesn't take this thing to tip over very far, right, before the center of gravity is outside the area of the base and it's going to fall down. Right, now then, that's just the jumper. We set Scott on top of it.
It's
So what happens to the center of gravity now? It moves up, just like
the
when I
thing.
take this thing, right? Here it's pretty stable, but if I turn it over and move the center of gravity up, it becomes very unstable. So, let's move over here. Scott,
Yeah.
we want you to sit down there.
All right.
No, you got to sit around the other way.
All right. Ow.
Put one foot on one side of the runner, one foot on the other side of the runner. Don't fall over. Now then, if you're going to go downhill, what are you going to do? You're going to pick your feet up, right? Because
Yeah.
you're going to let your feet slide. Pick your feet up. I'll hold you. All right? I'll hold you. I'll hold you. Okay, so it's very unstable. And what you have to do, if you're a real skilled rider, and we didn't have too many people that were, is you pick your feet up off the ground, and then to keep your center of gravity right straight over that base, you move your legs up and down a little bit, right?
Yeah.
If you so that keeps you balanced, right? And you have to do a lot of practicing to be able to ride it. Okay, you can get up off of that thing now
All right.
before we fall down and hurt ourselves. Okay. So the key to success here on MCAS is not to try to remember the answers because they're not going to ask you that question again. But what you need to
Center of
do
gravity.
is understand the concepts behind whatever the science or the technology is, right? And then you can take that and you can apply it to any question they ask you. If you ask now, why does that Eiffel Tower not fall down? Why doesn't it fall down?
Because the center of gravity is pushing down.
Because the center of gravity is still, when we take the force, gravitational force, is still somewhere inside the base on the Eiffel Tower. Right? If it moves far enough over
It falls.
to where that force comes outside the base,
Gonna fall.
it's going to fall down. We're going to have a lot of used brick. Okay? So, very simple. And how do we find the center of gravity? Pretty easy, like our snowman with the spaghetti stripes, right? You take a couple places like this, right? Draw a line straight down through the center of gravity, in that case. Go to the other side, draw a line straight down through there, and where the two lines intersect, right, somewhere in this center of this piece of paper is the center of gravity, which in our case is somewhere right in here. Right? If we could have, do we have to do it with these arms? No, we could have put a string here, right, and draw a line straight down here like this, or and one here, and draw a line straight down here like this, and we would end up with the
Center of gravity.
center, and it would have been in the same spot, normally. It would not have moved. All right, so you're all ready for MCAS now, right?
Hey.
Very good. All right, that's it for today. I hope everybody goes home and builds a Yankee jumper and enjoys the snow.